Okay, so today we're jumping into something that feels like it's pulled right out of a sci-fi movie, 3D bioprinting. Yeah, I'm talking about the incredible science of actually engineering and printing living human tissues. It's happening right now. And really, this whole field boils down to one single massive question. What if? What if we didn't have to wait for an organ donor? What if we could just print a new kidney or a new patch of skin on demand? I mean, could this technology completely change medicine as we know it?
Well, the answer is a pretty stunning yes. I mean, look at this. It's already happening. What you're seeing here is a process where a special liquid gel, they call it a bioink, which is just packed with living cells, is being solidified by a super precise pattern of light. It's building a living structure, one incredibly thin layer at a time. So the real question is, how on earth does this actually work? All right, to really get this revolution, we've got to start with the big idea that makes it all possible in the first place. Welcome to the world of tissue engineering. The entire goal here is to create living, working tissues. And the secret sauce is the bioink. Now, this isn't just some fancy goo, it's a super carefully designed environment. It's a mix of living cells that are suspended in this special biocompatible gel that basically acts as a scaffold, giving that new tissue its shape and its structure while it grows. So you've got this liquid bioink. How do you turn that into a complex living thing? To figure that out, we've got to take a peek inside the machine itself. We're going to focus on one specific method called digital light processing, or DLP. Now, you might picture 3D printing as a nozzle squeezing out material, kind of like a tube of toothpaste, right? Well, DLP is totally different. It works by projecting an entire 2D image all at once into a vat of that liquid bioink, hardening a whole layer in just a few seconds. This makes it insanely fast and lets you get unbelievably high resolution. So check this out. You can see the entire journey the light takes. It starts from a source, like an LED, it gets focused and shaped by a bunch of lenses, and then it's bounced around by mirrors. But the real magic, the part that makes it all work, happens at one very specific component, right in the heart of this optical path. And here it is. This is the digital micro mirror device, or DMD. You should think of it like a computer chip that's covered in millions and millions of microscopic mirrors. Now here's the crazy part. Each one of those tiny mirrors can be tilted on or off thousands of times a second. So by controlling exactly which mirrors are on, the DMD basically becomes this dynamic, ultra-high-resolution stencil, creating the perfect shape of light needed for every single layer of the print. Of course, this whole physical process is driven by what's happening on the computer. You start with a normal 3D model. The software takes that and turns it into a grid of 3D pixels. We call those voxels. Then that voxel model gets digitally sliced into thousands of super thin 2D layers. And each one of those slices gets sent to the DMD as a picture, which is then projected into the bioink to build the real thing, layer by precise layer. Okay, so the technology is there and it works. But building the machine is one thing. Actually using it to manufacture medical products that are safe, effective, and consistent every single time, well, that's a completely different ballgame. And here's why. This is the really crucial point. We're not printing with plastic here, we're printing with living cells. And life, by its very nature, is variable. Every batch of cells is just a little bit different. And on top of that, it's expensive, there's a serious lack of sensors to monitor things in real time, and the way we test for quality is often slow and destructive. I mean, you literally have to destroy the tissue you just printed to see if it was good. All of this makes going from a cool lab prototype to actually producing these things at scale a massive, massive headache. This right here is the fundamental challenge of biomanufacturing. It's not about proving you can print something cool once. It's about building a process that can print the exact same, high-quality, safe tissue thousands of times, without fail. And that requires a totally new way of thinking about how we make things. So to solve this monster of a problem, engineers are finally moving away from the old trial and error approach and shifting towards something way more systematic and intelligent. It's a concept called quality by design, or QBD for short. Now, instead of just printing something and then running a bunch of tests to see if it worked, QBD completely flips the script. It starts by defining exactly what the final product needs to be. How strong, how big, how many living cells. Then you work backwards to identify and control every single variable in the process that could possibly affect that final result. It's about being proactive, not reactive. And this framework explains it perfectly. Over on the left, you've got your inputs, your critical material attributes, things like the purity of your cells. Then in the middle, you have the process itself, with its critical process parameters, things like the bioink temperature or how intense the light is. The whole idea is that if you can precisely control all of your inputs and your process steps, you can basically guarantee that you'll hit your desired critical quality attributes, the final product's properties, every single time. You're building the quality in from the very beginning. Now, the set of tools that actually makes quality by design possible is called Process Analytical Technology, or PAT. The best way to think about it is that you're giving the bioprinter senses. You're giving it eyes, a sense of touch, by embedding real-time sensors right into the manufacturing line. So instead of taking a sample out to test later, PAT is measuring things like pH or cell density live as the tissue is being printed, which means you can make automatic adjustments on the fly. But as you can probably guess, sticking these sensors in there is a gigantic challenge. And this really shows you why. See, monitoring things at the big, macro level, like the overall temperature of the whole vat of bioink, that's pretty straightforward. But as you try to zoom in to get down to the microscopic level, to, say, monitor the health of a single cell inside the scaffold, the complexity just goes through the roof. So, where is all of this headed? I mean, how do we actually overcome these huge challenges and unlock the real, full potential of bioprinting? Well, more and more, the answer seems to be artificial intelligence. Machine learning algorithms are getting really good at analyzing the insane amounts of data pouring in from those real-time sensors. For example, there are AI models that can now look at microscopic video of the bioink before you even start printing and accurately predict how strong the final tissue will be. It's kind of like knowing the outcome of a race before it even starts, which lets us boost quality and consistency like never before. And believe me, this technology is moving forward at an absolutely incredible speed. We're already seeing new DMDs with 4K, even 8K resolution, which is going to let us print tiny, intricate biological details like blood capillaries. AI feedback loops won't just predict what's going to happen, they'll correct tiny little errors as they occur. And pretty soon, printers will be able to switch between multiple bioinks on the fly to build complex tissues with all different kinds of cells, all while new printing methods make the whole thing faster than ever. Which, of course, brings us all the way back to that first question we asked, but now on a much, much grander scale. This technology is literally giving us the tools to design and build with life itself. And that forces us to ask a much bigger question. What are the limits? And what will we choose to build next?